So, in this lecture we will learn about find algorithm. The algorithmic issue that we are interested in is the following. The input is a set S of integers and a number k, which is also an integer, okay, positive integer, and we have to find the kth smallest element of S. The straightforward approach for solving this would be to sort S and output the kth element, but that would take n log n time. So, sorting takes n log n time. Question is, can we do it better? Of course, there are linear time algorithms, linear time deterministic algorithms to solve this problem. We will see a simple randomization. The linear time algorithm, which the deterministic linear time algorithm is a little more complicated. So, we will see that a simple randomized algorithm can do this job. And while doing, we will also learn about probabilistic recurrences. Okay. So, let us look at that. So, our algorithm is, the steps are as follows. First, we pick a random number y from S, and based on this randomly chosen number, we split the entire set into two parts. It is a very natural thing to do. The set of numbers which are smaller than y and the set of number which is greater than y, and based on the number of elements in this set we recurse. That is the basic idea of the algorithm. Okay. So, we will construct sets A and B based on S. So, A consists of elements less than elements of S less than, let us say y, and B is the set of elements of S greater than y. And the third step would be, so if size of A is equal to k minus 1. So, we will assume for the time being that S contains distinct elements, there are no repetition of elements. So, if A contains k minus 1 elements, then return y as the answer. The next condition would be, if size of A is less than k minus 1, that would mean that the kth smallest element is not the element that we have chosen, it is in the set of elements which are greater than y. So, we will say return, we will call this algorithm as find S comma k. So, here what we will return is return find B. So, in B we will find the k minus size of A plus first element. So, already we have identified mod A elements which are less than the kth smallest elements, and the element y chosen is also not the kth smallest. So, all those elements are gone. So, we will return from B. The third condition would be, if A is greater than k minus 1, then we know that our element basically lies inside A. So, we will return find A comma k. okay, simple natural algorithm. So, if our collection was say 2, 8, 3, 9, okay, so this contains 7 elements, and if we wanted to find the fifth smallest element, suppose we randomly choose 3, then so suppose y is equal to 3, okay, and based on 3 if we split, we have our A is equal to the set consisting of 2 and B consists of every other element. So, 8, 9, 7, 16 and 4. Okay. So, we know that the fifth largest must be in this collection in B, and it must be the, so we will basically find the third smallest, because the first two small elements are basically in A and Y, find the third smallest in B. So, B comma 3 would be the call, and again let us say we choose a random element, suppose we had chosen let us say 9. Okay. So, in that case our A would essentially be 8, 7, 4 and B would just contain 16. Okay. And there are already 3 elements in this collection. So, we can skip all the other elements. So, we will basically do a find A, where A is now 8, 7, 4. So, find the third element in A, and the recursive call would return 8 as the fifth largest element. The answer is correct, 1, 2, 3, 4 and this is the fifth element. So, that is our algorithm. How do we analyze this algorithm? Okay. The worst case running time of this algorithm can of course be very bad, but what we want is the expected running time of this algorithm. Okay. That could depend on k. So, what we will do is we will define T n comma k as the expected running time on any input. I mean the worst case expected running time for an input of size n, and we are interested in finding the kth smallest element, and we can define T n to be max over all possible values of k T n k. Okay. So, amongst all possible k's, whichever k is the worst k for n, the value of T n k at that point is T n. Okay. So, let us write down a recurrence for T n. Okay. If you had an input of size n, how much time does it take in an expected sense? So, we had the following situations. If the element that we pick is the kth smallest element, we could be very lucky and we could just pick the middle element. All those elements have to be compared with all the other elements. So, after this step, after this pick, this construction of A and B could take n minus 1 comparisons. In all cases it takes n minus 1 comparisons, and after that we require additional comparisons, one of these comparisons, and the cost of those comparisons will be based on our choice y, and we have to find the average value over all possible choices. So, with probability 1 by n, we could just require one comparison, okay, and each of these other choices could happen based on the number that we have picked. So, suppose, so let us look at these sets A and B in their sizes. So, based on the split, we could have either the size of A as 0 and B as let us say n minus 1. Both of them are, I mean, so this will depend upon which is the k, which is the y that you have picked. It could also be 1 and let us say n minus 2, 2 and n minus 3, n minus 1 and 0. So, all these could be equally likely with probability 1 by n. Once again, the pivot that we pick or the element y that we pick will uniquely split the entire set into A and B, and size of A could be 0 to n minus 1, size of B also could be 0 to n minus 1. Once the size of A is fixed, the size of B is automatically fixed, and all these are equally likely. Let us look at the case where this is of size I and this A is of size I and B is of size n minus I minus 1. Okay. Now, in this case, whether we recurs in I or whether we recurs in n minus I minus 1 depends on the value of k. Okay. If k was smaller than I, then we would have recursed in A, otherwise we would have recursed in B. But since we are taking the average over all possible, we are interested in finding the worst case behavior over k, because here we are looking at max over all possible values of k, we could assume that we will be always, we could be very pessimistic and we could say that always we will be recursing on the larger set. Okay. So, this can be and therefore, whenever we are confronted with the choice of 0 n minus 1, we will basically be recursing in n minus 1. Whenever we are confronted with the choice of 1 n minus 2, this is where we will be, and all the way up to let us say roughly n by 2, we would be recursing in the other half. And if you look at it carefully, the terms basically repeat. So, we can say that T n is equal to n minus 1, this is for the fixed comparisons that you have to make to separate the elements into sets of size, sets which is smaller than y and greater than y, plus if you are lucky you could take, let us say, with probability 1 by n, you have to take just return the correct answer. So, let us say that is constant time. So, 1 by n into 1, or if we are looking at the number of comparisons, we could just say that this does not happen at all, plus 2 by n into T n minus 1. So, T n minus 1 appears in both these situations. So, that is why this 2 is coming. So, all these could appear, the possibilities for A and B, each of them appears with 1 by n probability, but 0 n minus 1, in that case we recurse on the set of size n minus 1, and n minus 1 0, again we recurse on the set of size n minus 1. So, that accounts for 2 into T n minus 1 plus T n minus 2 all the way up to let us say T n by 2. Okay. So, this is the recurrence that we have. T n is equal to n minus 1 plus 2 by n times summation T I varying from n by 2 to n. Okay. So, if you look at these, the summation, there are precisely n by 2 terms or n by 2 plus 1 term, something like that, and they vary from T I to T I plus, from n by 2 to n. Okay. So, we are going to guess that, we could guess and solve. So, let us check whether T n is less than or equal to 4 n. Okay. So, suppose we plug in the value that T n or T k is equal to 4 k is less than or equal to 4 k, we can see if this recurrence is satisfied. Now, if this recurrence is satisfied, then we know that T n is less than or equal to 4 k. Okay. So, when we plug that in, T I from n by 2 to n takes value from let us say 4 n by 2 to 4 n. Okay. So, this is precisely, this is roughly n by 2 terms, okay, and their values are varying from 2 n, or let us take the 4 out, 4 times n by 2 to n, and the average value of these is n by 2 plus n by 2. Okay. So, that is going to be 3n by 4. Okay. So, these are n by 2 terms with an average value 3n by 4. So, you can say that summation I equals n by 2 to n T I is approximately equal to 3n by 4 into n by 2, because there are n by 2 terms. You can do the calculation more precisely and check it, but this itself is sufficient for us. So, this tells us that T n is equal to n minus 1 plus 2 by n into 3n by 4 into n by 2. Okay, so, this cancels. So, overall you will get this as okay. So, there is a 4 here, 4 into 3n by 4. So, this is 4 times 3n by 4. So, 3n, so n minus 1 plus 3n, which is 4n minus 1. Okay. So, therefore, we can say that the average time taken is going to be less than or equal to 4n, which is a linear time algorithm. Okay. So, for this particular week, the things that we have covered, first we looked at quicksort algorithm. Okay. And then we had looked at another algorithm for matrix multiplication. And this was the third algorithm called find algorithm. Okay. So, all these algorithms used randomness in a certain way, but if we look at these algorithms closely, there are some differences between them. Quicksort, for example, always gave the correct answer. This find algorithm also always gave the correct answer, whereas matrix multiplication, we had this property that the correct answer is given with high probability. But the quicksort algorithm could have large running time in certain runs. Find algorithm also has that problem, the running time could be high. So, large running time is a drawback of this algorithm, whereas matrix multiplication was giving correct answer with high probability, but the running time was, to say, always good running time. In the sense, it would never take more than, I mean, the algorithm would always run in O n square. Okay. So, this basically is the two types of randomized algorithm. The first algorithm, which always gives the correct answer, is called a Las Vegas algorithm. Whereas, the algorithms which sometimes give an incorrect answer, they are called as Monte Carlo algorithms. Okay. Which one is better? Well, it depends upon our needs. If we wanted an algorithm which will always give the correct answer, if the correctness of the answer is paramount importance, then we will have to go with Las Vegas algorithm. But if we want the algorithm to be fast and we can live with a small, we can take a small chance of error, then Monte Carlo algorithms are usually used. Okay. That is all that we will have for this week. The next week we will look at axiomatic definitions of probability. We will have a review of probability that we would be needing in the later on lectures.